Hey there, and welcome. Today we're going to go on a pretty wild ride. We're taking something you see literally every day, a simple leaf, and we're going to zoom in, way in, to uncover a secret world of millions of tiny, moving mouths hidden right on its surface.
I mean, seriously, think about it. We see leaves everywhere. We know plants are crucial, right? They breathe in carbon dioxide and give us the oxygen we need to live. But how do they actually do it? If a plant breathes, where's its mouth? Where's its nose? It's a simple question, but the answer is totally invisible to the naked eye.
Well, the answer is these things called stomata. They're these microscopic pores, mostly on the underside of leaves. The best way to think of them is like millions of tiny adjustable mouths. They open up to inhale CO2 for fuel, and they exhale oxygen and water vapor. They're basically the bouncers at the club, the gatekeepers between the plant and the outside world.
Now, to really understand these amazing little structures, we're going to zero in on the leaf of a very specific plant, the durian. And we're not just going to look at one leaf. Nope. We're going to check it out at 3 totally different stages of its life, young, intermediate, and old, to see how these tiny mouths change over time.
Okay, so even before we bust out the fancy microscope, you can already see and feel some obvious differences. The young leaf, it's light green, thin, and soft. You can tell it's built for growing fast. The intermediate leaf, it's darker green, a little thicker. It's like the mature powerhouse. And the old leaf, it's kind of yellowish, thick, and hard. These clues on the outside are already hinting that they're doing very different jobs on the inside.
To actually see the stomata, though, your standard high school microscope just isn't going to cut it. We need a tool that's way more powerful, something that can map the actual surface of the leaf in 3D. We need an electron microscope.
So what's the big deal? Well, a light microscope uses, light. It's great, but you can only zoom in so far. A scanning electron microscope, or SEM, is a whole different beast. It doesn't use light at all. It shoots a beam of electrons to scan the surface of an object, and that gives us these absolutely stunning, detailed, 3D-like images. For seeing the actual shape of the stomata, the SEM is, hands down, the perfect tool for the job.
But hold on, you can't just stick a fresh, wet leaf under an electron beam. The sample has to be perfectly prepped so it can handle the process and show us its secrets. And it's a really precise, multi-step procedure.
First, they snip a tiny little square from the bottom of the leaf, because that's where most of the stomata hang out. Then it gets washed and put in a chemical solution that basically freezes its structure in place. Next up, they have to get every last drop of water out of it. And for the final step, and this is so cool, they coat the whole thing with an impossibly thin layer of metal, usually gold. That metal coating is what allows the electrons to bounce off and create that perfect picture.
Okay, our samples are prepped, they're coated in gold. It's time for the main event. It's time to slide them into the SEM and finally see what's been hiding on these leaves this whole time. All right, first up, the young leaf. Scientists look for a few key things here. First is density. How many stoma are packed into a tiny area? Then they look at the guard cells. Those are like the 2 lips that form the pore and decide if it opens or closes. For a young leaf that's all about growth, you'd expect to see a ton of these mouths wide open, just hungry for that CO2. Next, the intermediate leaf. Here, the name of the game is comparison. Has the density changed now that the leaf is bigger? Are the guard cells more developed, more mature? This leaf is in its prime. It's the main engine for the plant. So we're looking for a breathing system that's working at absolute peak efficiency.
And finally, the old leaf. Here we're looking for the microscopic signs of aging, of retirement. The density of the stomata might have gone down since the leaf isn't growing anymore. The guard cells themselves might look a little worn out. Maybe they're not as good at opening and closing. The whole system is just powering down as the leaf gets to the end of its.
Seeing these images, it's just mind-blowing, right? But the real magic happens when you start analyzing the data. What do all these differences in density and shape and how they work at each stage? What does that actually tell us about the plant's game plan?
So this is how scientists put it all together. They find that the young, growing leaf has a lot of small, mostly open stomata to suck in as much CO2 as possible. The intermediate leaf is the powerhouse. It has the highest number of mature, really responsive stomata. And the old leaf? It shows a lower density and less active stomata, because its job is basically done.
So the big takeaway here is this: form follows function. The microscopic design of the leaf surface isn't random at all. It is perfectly, absolutely tailored to do what that leaf needs to do at that exact moment in its life, whether that's growing like crazy, producing energy, or just getting ready for the end.
And that leads us to a really important question that this kind of science helps answer. Which stage is the most efficient? Which one hits that perfect sweet spot between letting in enough CO2 to grow, but without losing too much precious water? All the evidence points right to that intermediate leaf, the mature peak performance.
And this is what's so amazing. By looking at these tiny little details, we're not just learning about one durian leaf. We are getting a window into the entire plant strategy for survival, how it manages its resources, how it adapts to its environment, and how it's evolved to thrive over millions and millions of years.
And that brings us to our final thought. When we think about our own world, a world with growing challenges like drought, which strategy becomes the most important for survival? Is it the young leaf's go-for-broke growth strategy, or is it a strategy that's better at saving water? Understanding these tiny mouths could be the key to figuring out how plants, and maybe our entire planet, will adapt to whatever the future holds.